Welcome back to Applied Algebra and Trigonometry. Yesterday we talked about integer exponents and how to simplify fractions with integer exponents. Today we're going to be talking about fractional exponents. Here's your first example of a fractional exponent, a to the 1 over n, and it's equal to the nth root of a. Now you may be able to see the pattern that we're going to establish here a little bit better if I write in the exponent of a here. So a to the first power is a, and the nth root of a is a to the 1 over n. For example, 8 to the 1/3 could be rewritten as the cubed root of 8, which of course is equal to 2. And 4 to the 1/2 equals the square root of 4, or 2 again. Look at that. But fractional exponents can be even more useful because we can interpret a to the m over n. And when we do that, if we follow the pattern that's been established with our a to the 1 over n, we would have the nth root of a to the m, which is true. Let's analyze this rule of fractional exponents a little bit more. I think we can expand it. Because we have that rule that says a power raised to a power means you can multiply the powers, keeping the base the same, or exponents if you prefer that term. Now, looking at the rule we've already established for a fractional exponent, it looks like we can do the same thing. A to the m will be under the radical, and n will be the index of our radical. But if we think about it, this same rule of exponents that we've used before allows us to rewrite this in this way. Because when we perform the multiplication, we will still get m over n as our exponent. So it is also true that the nth root of a raised to the mth power is equivalent to a to the m over n. Why would we want different forms of this? Let's look at an example. And let's interpret this two different ways. Which one appears most useful to you? I would argue it's the one on top, because I know that the square root of 9 is 3, and then if I raise that to the third power, I get 27. I can do that without a calculator. Cubing 9 to get 729 takes a little more effort, and then the square root of that, oh yeah, I'm going to the calculator to get 27. Either way, you get to the right answer. It just so happens that this configuration seems to be a little easier to me. Here's a tricky one. There are a lot of negatives in there. So let me make sure that I know which negative goes where. Is the negative here in front of the 7 raised to the negative 1/2 power? No, it is not. So I'm going to put parentheses around just the 7 and raise it to the negative 1/2 power. Please remember, of course, that this negative can be interpreted as a -1. That may help you with our next step, because something needs to remain in the numerator there. Usually it's a 1, but in this case it's negative, so -1. When our 7 to the negative 1/2 migrates to the denominator, and the exponent becomes positive. Now, I'm done with the numerator here. Let's look at the denominator. 6 to the -1. Because it's already in the denominator, that negative drives it to the numerator with a positive exponent. And our 7 to the 1/2 that was originally in the denominator stays there. So -1 times 6 to the first power is -6. And in the denominator, 7 to the 1/2 times 7 to the 1/2 becomes 7 to the 2/2, which is 7 to the first power, or just -6/7. Are you ready for a challenge? Whoa, decimal exponents? let's get rid of the negative exponent first. What, we can do that with decimal exponents? Absolutely. Your negative exponent will still drive the base to the opposite position in the fraction, the denominator in this case, and your exponent will become positive. But I'm still not loving those decimal exponents, so let's convert them to fractions. So 4/10, just by saying it tells us what fraction to write, 4/10, 4/10. But we need to reduce that to make it 2/5. And then 5/10 is the same thing as 1/2. 0.5 is 1/2. When we rewrite our expression with these fractional exponents, it becomes a little more clear. Now the question becomes, how should we interpret this 2/5? Let's see, do I want to do 32 squared first? I don't think so, because I've memorized that the fifth root of 32 is 2. But I'm going to rewrite it this way first, so that I'm taking the fifth root and then I'm squaring that result. And then over here, I just have the square root of 25 in the denominator. Please remember, I'm not solving anything here. I'm evaluating what was given to us, what was written in this fashion. There's no indication that they want a plus or minus here in front of the square root of 25. So I'm only going to be dealing with positive numbers like 1/5. So that brings us to 4 and 1/5, which is okay, except when we began this process, we were looking at some decimals in the problem that we were given. So let's convert this to decimal form. And by the way, as an improper fraction, this is equal to 21/5. And if you do that division, you're going to find that our final answer is equal to 4.2. Because I started with decimals, I'm going to end with decimals. So that was a bit of strangeness there compared to what we've been doing, moving from a decimal exponent to a fractional exponent and dealing with the negative and then converting everything back to a decimal. So how would you go about checking this to make sure it's correct? There's no x. We can't substitute 4.2 for an x and see if it works out. So let's just take this original expression and put it into the calculator. What would it look like, though, when it went into the calculator? Well, for your calculator, it would look like this. Here are a few things to note about your calculator. The 0.4 was not necessary. Your calculator senses that decimal point there just fine without the warning 0 in front of it, so it just drops it. And here you have a negative 0.5 or a negative 0.5. Make sure when you are typing this in that you use the negative sign at the bottom of your calculator and not the subtraction sign. Your calculator gets very touchy about that. And here's our answer. It checks. So I probably should have mentioned that the instructions for all of these examples were to evaluate the expression you were given. So let's take a look at this one. 750 to the 2/7. What's the 7th root of 750? Do I really want to square 750? Nope, I'm just going to plug it into the calculator. But when I am plugging this into the calculator, I'm going to have to be careful. If I do not put parentheses around that 2 divided by 7, my 2/7 exponent, the calculator will return a very different answer. Let me show you what happens. First, if I put it in correctly with the parentheses in place around the 2/7, and then if I do not put any parentheses around that. So you see, we get very different answers. Be careful with your parentheses. So our evaluation of this problem should be that 80.5 times 750 raised to the 2/7 power is equal to 534. And just for your information, this calculation will give you the temperature in Kelvin for a gas at a pressure of 750 kilopascals. Hey, it's an application class. I couldn't leave it with just a bunch of numbers. One last example. here we have everything written out as a fraction. What do I notice first? I notice I have a negative, so I'm going to get rid of that. This would be equal to x to the 1/5 times x to the 3/10 divided by x squared. Well, would you look at that? They're all the same base. That means I can, when I'm multiplying, add the exponents, and when I am dividing, I can subtract the exponent. So now I have some arithmetic to do. I'm going to take all of those exponents, 1/5 plus 3/10 minus 2, and I'm going to combine them. I have to find a common denominator. That will be 10. So 2/10 plus 3/10 minus 20/10. So 5 minus 20, negative 15/10 is what we get when we add up all those numbers. But that is equal to negative 3/2. And that's the same thing as 1/x to the 3/2. And that's it. So this was a brief introduction into working with fractional exponents and moving between fractional exponents and radical notation. We're going to be doing a lot of that over the next few classes, and we will be applying all of the rules of exponents that we've been working with. So please practice, practice, and practice some more. And I will see you in class.